Well, hello there. So let's do some circuits today. The goal for today is to look a little bit more in depth on Ohm's Law, which we saw before, and then introduce Kirchhoff's laws, which we'll be using throughout the semester. So again, these slides are mostly taken from our textbook, although I've edited them quite a bit from that starting point, but just to give some acknowledgement to the source. Okay, so Ohm's Law you've seen before, I'm sure. V equals IR is our baseline Ohm's Law. Voltage we know about, and current we know about. Resistance is a material property. It's how hard it is to push electrons through a material. So it has to do with the property. So there's a table in the book of different resistances for different materials like gold versus steel or copper. And then it also depends on the cross-sectional area. The more material you supply, the less resistance you'll get. So you can calculate the resistance given a material and its cross-section area and its length. So Ohm's Law, when we use it in this class, we're using it to solve circuits problems. And we have to be very careful with the sign convention because current has a direction, shown with an arrow, and voltage has a polarity, shown with a plus and a minus. And Ohm's Law is V equals IR only if the current goes from plus to minus. That's our passive sign convention, if you remember from earlier lectures. So often in a circuit analysis, we don't know the voltage and we might not know the current. So we're guessing. It's like a free body diagram in statics where you pick a reaction direction. If you get it wrong, the sign changes. So here, sometimes we'll draw a voltage, or it will be given to us with the polarity opposite to what's shown here. Then if you flip the polarity on V and keep the current going this way, then V equals minus IR. Same thing if you flip the current direction and keep the polarity the same. So if the current goes from plus to minus, V equals IR. If the current goes from minus to plus, V equals negative IR. So keep that in mind. That's our first point here. The second thing is often we're doing node voltages. Ohm's Law is set up for the voltage across a resistor. But if we're referencing voltages to ground, like a node voltage, then that's not necessarily the voltage across the resistor unless the minus terminal happens to be ground. In general, it's the difference of the node voltages that's the voltage across. So VAB is VA, the plus voltage, minus VB, the minus voltage. So once we label plus and minus, so we can get the Ohm's Law polarity, we know which one to subtract from the other. And we get an equation like this. This is I equals V over R, but V is the difference of the node voltages. We'll review those as we get into node analysis, but try to get those habits set right now if you can. So when you take the circuits lab and you build parts, resistors are labeled with these color codes that go back a long time. So there's a chart here you can look at and memorize if you wish, but the first few stripes are the numbers, and then there's a power, a multiplier stripe that comes in. Brown, black is 1, 0. So if you're looking for a 1K or a 10K or a 100K resistor, it's going to start with brown, black. The other option is to measure with your voltmeter set to resistance to be a resistance meter. You can measure the resistors. If you can't see the colors very well, sometimes they're poorly marked. Make sure you pull one end out so you measure just the individual resistor and not whatever it's plugged into as a circuit. There are other forms of resistors. This table shows things like thermistor is a sensor where the resistance changes with temperature. We'll use those in the instrumentation class, ME360, next fall. Piezo resistance is something that changes resistance with pressure, so sometimes those can be used for touch sensors. And then we have these variable resistors. A rheostat is a two-terminal variable resistor where we have some stretch of resistive material and we tap into it somewhere. So they call this the wiper. And so this is a variable resistor that the resistance between terminal 1 and terminal 2 is set by a knob usually, or a slider maybe. More commonly is the potentiometer, because you can use it as a rheostat or as a voltage divider. This is a 3-terminal device, so it has one big long resistor and a terminal at each end, plus a tap that goes into the middle, the wiper. And so the way this works is between 1 and 3, you get your basic rheostat function where, depending on the knob setting, you get a resistance between 1 and 3. That's a fraction of the total. But then between 3 and 2 is the other half. So if this is a 100K potentiometer, then 3 divides this could be, say, 30K and 70K, or 50-50, something like that. The total has to be constant, but the wiper sets the divider. This is really useful if you need a voltage instead of a resistance output. So if you put a voltage here and ground here, then this center terminal will vary between the max voltage and 0 volts depending on the knob. So these are very commonly used for volume controls on all kinds of audio equipment, but also as a really useful sensor to measure angles, and you can have sliding ones. So don't discount the potentiometer as a very useful analog sensor. Since we're talking about resistance again, I think we saw this on a previous lecture, but remember, an open circuit or cut wires can be modeled as an infinite resistance. So we can talk about this resistor being in parallel with this resistor that's infinity, and we can apply the equivalent resistance formulas that we'll see soon. And same thing with a short circuit. You could think of that as a resistor with a value of 0, and then you can do all of your analysis using 0 in there and see how the circuit turns out. Okay, so now we're going to start with Kirchhoff's laws. Notice that there are 2 H's next to each other in Kirchhoff. It's a very common thing to drop an H and misspell it. And in fact, if you Google for Kirchhoff's laws with 1 H or with 2 H's, I think you get about the same number of hits. So, but it does have 2 H's, and I sometimes misspell it myself, so try to remember that. There are 2 Kirchhoff's laws, and they're basic conservation laws, saying that energy isn't created or destroyed, or in a system we conserve energy. And so we have the Kirchhoff's current law, which we'll abbreviate in this class as KCL, and Kirchhoff's voltage law as KVL. Hopefully you saw these in the physics class. That's the prerequisite for this class, but we'll do them again. It's worth seeing. These are really powerful. Kirchhoff's laws and Ohm's laws form the basis of all of our solution methods going forward. So with those 3 laws, KCL, KVL, and Ohm's law, we can do all the analysis coming up. So this is Kirchhoff's current law, KCL, and it can be written a few different ways. The most common is this bottom one: the total current entering a node equals the current leaving the node. So the current in equals the current out. That's the way I usually write it in this class. You can also say that the sum of the current entering a node is 0, and then it's positive if it's entering, and negative if it's leaving. That's going to give you the exact same equation here, no matter how you write it. Very importantly, you can't write Kirchhoff's current law for a node until you draw a picture. You need a free body diagram or some sketch of this node, and you have to label the currents and you have to give them arrows. We have to decide if this is going in or out. If you just write I1, there's not enough information to know if you got it right, because in versus out flips the sign or flips which side of the equation on these 2 sign conventions. So before you can apply Kirchhoff's current law, you have to assign a direction to the current in each branch as it hits that node. So make sure you do that. It's a very common mistake that people will do an analysis and just write I3, and in their head they know what it is, but if they get it wrong, I just have to assume they don't know what you're doing. So always draw arrows before you do Kirchhoff's current law. So Kirchhoff's current law here, using the sign convention, entering is positive and leaving is negative. We have I1 entering and I4 entering, so those are positive. I2 and I3 are leaving the node, so they're negative. So this And then don't forget to write equals 0 when you're writing your systems of equations. The other form is shown here. This is current in equals current out. So I1 plus I4 are going in equals I2 plus I3 going out. This one sometimes is a little more intuitive in terms of physical. If these are big, then these have to be big in response because the node can't store any electrons. So it's a conservation of current kind of equation. But you can see that you can write this equation in this format. They are exactly the same equation in the end. So here's an example of a circuit to analyze. And we're given V4, the voltage across the 4 ohm resistor, shown here as 8 volts. And we want to find I1, shown, see, with an arrow going down, and I2. So I'll preface this by saying, at this point, we don't have a really methodical approach to solving these systems. So we know we have Ohm's law, we have Kirchhoff's current law, and we'll have Kirchhoff's voltage law in just a second. But we don't have node and mesh analysis, which are going to be step-by-step process. So at the end of this class, you'll be able to do this much easier than right now. For now, we're just going to throw a bunch of equations at it and see what sticks. So we just learned Kirchhoff's current law. So we can do that at node 1 here. And we've got 10 amps coming in and I1 going out. And then for this branch, there are a bunch of components in series. So when they're in series, elements in series have the same current. So I2 is labeled down here. And so it's going to be the same. I2 is going to round this corner and go up and go through this voltage source and then up through this 2 amps, also I2, and then go through this 1 ohm, also I2. So I2 is going in to node 1. And we don't need to have a new unknown defined because these are all in series. So if we draw this node, we have 10 coming in plus I2 going in equals I1 going out. So we look at that, and do we know anything? We're trying to find I1 and I2, so we need more information. We have one equation and 2 unknowns right now. So the other equation we've used is Ohm's law. So let's see what that will give us. And so if we try a few things, we have I2 here, and we know the voltage across this resistor, this 4 ohm resistor. So we can calculate I2 using Ohm's law and the known voltage. But be careful here because I is V over R. Everybody knows that. But notice the sign. I2 is drawn from minus to plus. So that's the backwards of our normal sign convention for Ohm's law. So I2 equals negative V4 over R. So negative 2 amps. So we really have 2 amps going from right to left. We've drawn I2 going from left to right, so it's negative 2. So we could flip this and change everything, but the proper way to do it is just carry on. It's okay to have a negative current. And once we know I2, then we can go back to this equation and solve for I1. So that's an approach. We're using our laws. We have to kind of hack around and see when do we use Kirchhoff's, when do voltage, Kirchhoff's current, Ohm's law, but we'll get these systematic techniques in the very next module. Okay, so the other Kirchhoff's law is Kirchhoff's voltage law, and it is written around a loop. So you need a closed loop, and the sum of the voltages around this closed path, this loop, is 0. So if you think of this as pressure in a hydraulic system, the voltage sources are pumps adding pressure, or if they're wired up backwards, reducing pressure, and then we've got losses from in the pipe, from friction in the pipe or orifices or something, and so the pressure increases and then drops and then increases and then drops, and when it comes back to the beginning, that must sum to 0. So it's a conservation of potential, in this case voltage, and around a loop. So you have to show, so we label the voltage across every element, so voltage sources are already labeled, but resistors and current sources and anything else, you have to pick a name and a polarity. And you have to show the polarity or else you can't write Kirchhoff's voltage law. the sum as we go around, we have to know which ones to add and which ones to subtract. So we have to go in a circle. Clockwise is traditional. It'll work if you go counterclockwise, but just go clockwise because that's the way all of these are going to be shown. And then we have to pick a polarity, a sign convention. And so the book's sign convention is different from, it's backwards. It's arbitrary, and it's backwards from every other time I've taught this class. I've used the opposite sign convention, but they wrote it down in this book, so we're using theirs. And I'll try to make sure my notes are consistent. The equations work out no matter how which one you adopt. Once you're finally done, you'll get the same equation. But here's our sign convention. As we circle the loop, we look at whether we hit the positive or the negative polarity first. So do we bump into a plus, or do we bump into a minus? So here we're going clockwise around, so we hit the plus on R1, so we would add V1. And then as we keep going around, we're hitting the minus on V2, so we subtract V2. So plus means add and minus means subtract, which is a nice sign convention, easy to remember. The reason I used the other one before is because when you write these things, here we're subtracting the 4 volt because we're coming up as we come through the loop, where this is actually supplying energy, but we're subtracting. Anyway, it matches our passive sign convention this way too. So so we would subtract 4 volts, we would add V1, subtract V2, subtract V6. Now we're coming down because we're going in a circle, so we add V3. So notice on the left, we add V1 and it's got minus on the top. On the right, we're adding V3 and it's got plus on the top. So remember, we're going in a loop, and then we're going to subtract V4 as we go along. So the polarity on left and right and top and bottom is different because we're going clockwise. So practice that, write them all down. You can pause the video. Did you get this answer? So here's minus 4 plus V1 minus V2 minus 6 plus V3 minus V4, and don't forget to write equals 0. That's Kirchhoff's voltage law. So be very careful. Make sure, again, you don't just write V2, but you write down a plus and a minus. If you don't know what it is, guess. Just put something down so that if we get a negative number, we know that the polarity is actually wrong, or the opposite way. Okay, so those are our basic laws, and we will see more applications of those in resistor circuits in the next video. The next module is where we'll really start the systematic approach to solving circuits. So I'll see you in the next video.